Hello, my name is Aleksandra Chrabrowa. I work at machine learning research at Allegro. And today I would like to present to you how we can learn the structure of customer service data at Allegro. And here is the plan of the presentation. I will start with the introduction. I will talk briefly about Allegro as an e-commerce company and the role of machine learning research team at Allegro. Then I will tell about our business case, which is customer service automation, and I will briefly describe its solution deployed in production, which is our intent discovery pipeline with human in the loop. After giving the overview of our system, I will describe in detail more detailed experiments regarding one part of it, which are representation learning experiments. These experiments have two key aspects. First, experiments with training schemes, and second, experiments with adding more data. And I will finish with summary and references. So let's start with the introduction. Allegro is the largest e-commerce company in Poland. There are over 13 million active buyers, 250 million offers, and 130,000 retail companies operating at Allegro. And to put it shortly, almost everybody in Poland knows what Allegro is, and most of people are its customers. When there is a big company with a lot of data, soon there is a need to apply machine learning techniques to it. At Allegro, we have machine learning research team. We operate in natural language processing, computer vision, and reinforcement learning domains. We do both research and applied machine learning. We publish open source code, and we write research papers. Team I work in, customer experience robots, automates customer service at Allegro. And in terms of scientific focus, it is pretraining and evaluating large language models, semi-supervised clustering, and human-in-the-loop NLP. And today I will present to you one of our solutions, which is intent discovery solution. And these are the researchers that contributed to these particular solutions. This is me, Aleksandra Chrabrowa, Timur Gadelia, Dariusz Kajtoch, Robert Moczkowski, and Piotr Rybak. Okay, so let's state the business problem now. So at Allegro, we have a customer experience department, which supports Allegro's clients and merchants. Everybody can write via chat or via email to Allegro customer experience, and they are supposed to receive our answer which explains something or solves the problem. And here is a sample question. The original language is in Polish, as most of our communication customer service. I will read the English translation. Hello, on October the 8th, I bought a case for headphones. So far, I have not received the goods. The seller is only surprised that I did not receive the goods. Besides, his account was blocked. Allegro participated in the discussion. I would like to use the buyer protection program. Best regards. And if you want to automate customer service for this query, it would be one way to automate it is to classify it as within the classification. I want to use buyer's protection program, and to present to the customer service worker an answer template to this particular question. However, such solution to the problem does not only require training a good intent classifier. Before, we need the taxonomy. We need to answer the question, how do we build the list of existing questions intents to customer service? How do we give meaningful names to these intents? And this leads us to the problem of open world intent discovery, where we have some data from customer service, all the questions to the customer service, and we have some labeled intents with examples, and we know that in this data, which is unlabeled, there are both known intents and unknown intents, and we want to somehow group and discover these unknown intents. And here is our intent discovery pipeline, which is deployed in production. And here is here's its architecture. It uses human-in-the-loop paradigm, and I will describe it in detail, all the elements one by one. So first, we have representation learning. We want to use both labeled and unlabeled data to learn representation of the text. This is the crucial part of the pipeline, which influences all other elements. And we usually start from a pre-trained BERT-like encoder. Then we cluster the representation we have learned in the previous step to obtain some groups of examples and to discover the structure in the data. This step is pretty straightforward. We use k-means clustering algorithm. However, the word overclustering needs some explanation because we don't know the exact number of clusters in the data, and we decided consciously to overestimate it, as we think that it's better to have two good quality clusters with the same intent rather than one cluster with multiple intents. Then we create meaningful names for the clusters. Before, clusters have only cluster IDs, and this might be difficult for humans to analyze them. We use multi-document summarization techniques to obtain one sentence that best summarizes a text in the examples. The next step is known intent prediction. As mentioned before, we have open world intent discovery setup in which our data may have some known and unknown intents in the data, which are unlabeled. We train a simple intent classifier, and we select only the clusters which have unknown intents, as they are interesting for our intent discovery pipeline. Once we have good selection of clusters with meaningful names and examples in them, here comes the human in the loop. Humans pick good quality cluster, which they think they are candidate for good intents. And later, humans annotate the data in these clusters, which were selected, to add new intents to the taxonomy. And finally, we have our defined taxonomy. We can train an intent classifier, and we can predict intents and answer templates in real time for customer experience department workers. And it is worth mentioning that this process is circular, that once we have a better taxonomy, we can start it again and do the intent discovery again in an iterative process. And I have described the pipeline as the whole, but in the next part, I will present the experiments on the representation learning part. The representation learning is the most important part of our system, and it influences impacts the performance of all other elements. And here are our representation learning experiments. So we have experimented with four 4 ways of training fine-tuning some pre-trained text encoder, for example, with BERT architecture, to obtain representations which can be used for clustering. And they differ in their complexity, and they differ in the fact whether they use labels or whether they don't need labeled data. The solutions which don't use labeled data are usually better at the beginning when we are only starting to create our taxonomy, and the solutions which use intent labels are better later on when we have some labeled data and we want to expand our taxonomy. So first, let's discuss the discussions which don't use labeled data. We can simply use static embeddings. This is very simple. We take our pre-trained text encoder, and we extract unsupervised text representation by simply average pooling the last layer. It does not need any additional training. It does not need even unlabeled data. And now, later, when we have here comes deep adaptive clustering, DAC, which also does not use labeled data. It can use labeled data, but the labels will be ignored. And this is unsupervised representation learning, and it uses contrastive loss. And to use contrastive loss, you need to have positive and negative pairs. And because you don't have labels, you define them distance-based. Simply, the positive pairs are the pairs which are the closest, and negative pairs are the pairs which are which have the biggest distance. And this distance-based definition is based on current state of the model. Let's move on to training schemes for clustering, which need intent labels. So first is supervised training scheme, just like for training the intent classifier. In this case, we need labeled data labels, and if we have some amount of unlabeled data, there is no way we can use it. We are using large margin cosine loss, and this is a simple classification setup. And finally, here comes the constrained deep adaptive clustering, Cdac. This method is semi-supervised, which means that it makes use of both labeled data and unlabeled data. And this method is an extension of deep adaptive clustering, when the same as in DAC, the examples without labels we construct from them pairs, pseudo pairs, based on the current state of the current distance of the model. And if we have labeled data, we are able to construct exact positive and negative pairs of examples defined on provided intent labels. So we make, whenever we have a data label, we make use of it, and if we don't, we try to construct a pair for contrastive loss in a different way. Okay, so I have described four training schemes, and now let's move to the results. So we have experimented with 4 training schemes: static, DAC, supervised, and Cdac. And for this, we need some data sets. So we have 2 types of data sets in our experiments. We have public data sets for intent discovery. We have banking and Cling data set, which are well-known data sets for this problem. They are in English, and in the table, you can get some notion of their domain by looking at the names of the classes from these data sets. And also we have constructed 3 internal data sets covering different domains of user queries to Allegro customer service, which is purchase, delivery, and retail. These are not all domains of queries to the Allegro customer service. We have just chosen 3, which we think were the most representative of the problem. And again, you can look at the table, the 3 sample class names, intent labels, to get some notion of what is in this data set. And I'm sure you will notice that the domain of these data sets is more narrow, that the differences are more subtle than in Clink or in banking. And for our experiments, we needed some pre-trained encoder to start with. And for English datasets, public datasets, we used BERT. And for Polish datasets, we use our own version of BERT, which is ALEBERT. So these were pre-trained encoders as a start from which we started our training procedure. We did 5 city runs, and we could not decide on the metrics, so we have chosen 5 metrics which we thought were relevant to the problem, and we computed the average. The average of the metrics is between 0 and 100. And the higher, the better. And to simplify this comparison, we computed the average for public datasets and for Allegro internal datasets. And here you can see the results. So first of all, looking at the public datasets, if we don't have intent labels, it seems that DAC, deep adaptive clustering, is better than using static embeddings. And the gain can be quite huge. However, the case is opposite for real-world internal data sets, where in fact this DAC training scheme does not add any improvement. And it's better to simply use static embeddings. We also notice that results for in our real-world data sets are much lower, which means they are probably more difficult. And again, we look at training schemes for clusterings which do not require, which use intent labels. And again, for public data sets, we can use simple supervised training scheme, which is better. And however, for internal data sets, our more complex training scheme, Cdac, constrained deep adaptive clustering, gives some gain. To sum up, real-world internal data sets and public benchmark data sets are sometimes different, and it's hard to make conclusions for real-world cases based on public benchmarks. And we have a hypothesis that perhaps it may be to the dataset quality and also to number of examples and to the class balance in the data. However, for internal data sets, for real-world data, we recommend Cdac training scheme. Okay, so this was the first part of the experiments in which we have evaluated popular existing training schemes, both on public benchmarks and on real-world internal data. And we wanted to move on from this. We wanted to improve the performance further. And we tried to do it by adding more data. Because maybe when there is some additional signal, our existing training schemes can benefit more from more data. And we have come up with 3 ways to add more data into our training. So first, before I was talking about only user question. We were only analyzing user question to the customer service. However, there is always a consultant's answer. And sometimes this answer may be better because it is written more, the consultant is paid to write it in a good way. It's more logical and well formulated. And when we have the consultant's answers, we have two ways. To add this answer and question. First, we can simply concatenate the question and answer text and use our models as we have previously used them. And also there are some more refined solutions. And actually, we have something like conversational Cdac, which is our own Allegro extension of Cdac training scheme, in which we have 3 separate heads for question, answer, and question, answer concatenation, which is reflected in the loss term, when we have, which is a combination of 3 losses: the loss for question, the loss for answer, and the loss for question answer. And different inputs are fed to different heads in our model. The second way to add more data is to use large amount of in-domain Allegro unlabeled data for first supervised pre-training of the encoders. So we are going one step back, and we are thinking what pre-trained models can be the starting point for our training. And we always take some public model, for example, Herbert, as a starting point. We take over almost 200 million messages from our internal data. We do mask language model pre-training with them. We obtain Alebert model. However, also recently Convert, which is contrastive pre-training objective, has become popular. And we continue training, mixing masked language model and Convert pre-trainings, and we obtain AleConvert. Also, we can we have another source of data, which are consultant stacks, which are weak label data. So it turns out that our consultants are allowed to add tags to user questions based on the internal taxonomy. We don't influence it. They can define as they want it internally. And we again start from Herbert, and we do multi-labeled classification pre-training with these tags as weak label data. And we obtain TagBird. And the results of adding more data in 3 forms: the consultant's answer, in domain unlabeled data, and consultant's tags are very encouraging. For all 3 ways of adding more data, we have noticed some improvement. So firstly, we can see that in this table with different pre-trained encoders, the results are getting better and better. We notice that the results for the Convert pre-trained encoder are better than from masked language model encoder. And we see that results for the encoder which uses these consultant tags, weak label data, are even the best. Also, when we compare the solutions which use only question and answer for each of the encoders, we can see that using adding answer also improves the results. So our recommendation is to simply use all the data you have. And this is the end of my talk. I would like to sum up that Allegro Customer Service Department supports clients and merchants. We want to automate this customer service and propose template answers. And for this, we need a taxonomy. Our intent discovery pipeline uses human-in-the-loop paradigm, and different training schemes are optimal for public benchmark datasets and for internal datasets. For internal case, which is real world, we recommend using Cdac. And when you have any additional data, the answer, large amounts of unlabeled data or weak labeled data such as tags, we simply recommend to use it.
Thank you, Ola, for a very interesting presentation. We have a couple of questions from the audience. So the first question, that is the most upvoted one, is as follows. Can you share how big Allegro's intent taxonomy is? Is it hierarchical?
Hello, can you hear me?
Yes.
I tried to share additional slide about the datasets, but I'm not sure if I accomplished this. Not really?
We can hear you, but cannot see you.
Okay, so I will answer not to make it longer. We have, in these experiments, we have 3 datasets, and they have between 20 and 110 intents. And the taxonomy is, our taxonomy has categories which are based more or less on the form which user selects when he asks a query. There's a simple form with categories, and later within these categories the taxonomy is flat. So each data set had flat taxonomy, we have chosen these data sets with varying number of intents to have a full picture of our business case. And of course, these 3 data sets do not constitute the whole Allegro taxonomy of customer service.
Okay, thank you. And the second question is, who are the people annotating the data for you? Do you use DataTarg, freelancers, or do your data science team annotate it by yourself?
We annotated internally. They are annotated by the customer service workers.
Okay, thank you. And the last question, you mentioned about 2 BERT-based models that are both produced by Allegro, AleBERT and Herbert. What is the relation between these 2?
Okay, so Herbert is available in public, and it is based on Polish corpora, so its domain is general. And AleBERT is internal Allegro model, which is based on customer service data. So this model is more domain specific. And when I was listing different language models, only Herbert is public and is general domain, and other are trained starting from Herbert, but using internal large amounts of internal Allegro data.
Okay, thank you. And that's all. These are all questions that we have collected. So thank you one more time, Ola. It was really interesting presentation.